This one is just algebra. So also, you have the answer key, don't you? I've given you the answers. So for A, when you do the answer key, all you're doing is isolating P. If you isolate P, it's a nice way to isolate it right there. What is it at? Can someone translate part B for me? What is it asking you to do in part B? Write a linear approximation. What does a linear approximation mean? Lena, what's it mean? Yeah, that means tangent plane. That's what this whole section's on. Tangent plane. So write a linear approximation, a tangent plane for the change in pressure, delta P, from the resulting change in temperature, delta T, and a change in pressure, V, delta V. So when you're trying to find delta P, and you're trying to find delta T, what do you actually, sorry, when you're finding these two, delta P and delta V, what are you actually finding? The what? What type of derivatives? You're finding partial derivatives. So for this one, what are you actually trying to find? Oh, you're trying to find partial P with respect to T, and partial, then the next one is partial P with respect to V. What's changing on this one? dP dt, what's changing? The T is changing. What's changing down here? The V is changing. These are the things that are changing. What goes on with all the other variables? Oh, they're constant, right? So you're doing two partial derivatives. You need two partial derivatives. Here are the partial derivatives. Once you have the two partial derivatives, what are you constructing? You're constructing the what? What are you constructing? The tangent plane. You're constructing the tangent plane, and you have an equation for finding the tangent plane, don't you? You've done it a bunch of times so far. What is that? Oh, it's going to be the partial with respect to t, dt, and the partial with respect to v, dv. Another way to say that is just delta v. This is the equation for a tangent plane right there. So all you're doing is plugging in. All you're doing is plugging in. So that's what you found in the first part of this. You found the two partials. Look where they go. This one marches down and is right there. This one marches down and goes right there. Does that make sense, everybody? Linear tangent plane. It's kind of strange in a way because when you think of linear approximation, you think of lines, right? Well, linear approximation is something that's slightly different in 3 dimensions. It's going to be with a plane.
So is there a difference between like this, that part with the equation, and you have like in 19, there's like another term?
We have traditionally, well not traditionally, so far we've been concerned with the rates of change going in which directions, with respect to y and with respect to x. But what did I start off by telling you? Well, when you're sitting at a point, yeah, you could go in the y direction, you could go in the x direction and look at the rate of change in each of those directions, but how many different directions can you move in at a given point in 3 space? Infinite number of directions. You could move in any direction you want, right? In one direction you might be going downhill, in one direction you might be going uphill, in one direction you might be going a little bit downhill, a little bit uphill. But the idea is we could do directional derivatives in any direction we want. So far we have looked at 2 directions. What are they? In the x direction and in the y direction. We need to be able to generalize though. We need to be able to find a rate of change in any direction. How are we going to do that? Well, as it seems to always be the case in derivative land, we love to start with the what? The what definition? What's it called?
Limit.
Yeah, the limit definition. So let's look at this for 1 second, right? No, more than 1 second actually. Is that totally dissimilar from other things you've seen before? Is that totally super new? No. It's a difference quotient, nice. What's different? What's specifically new about that statement that you haven't seen before? What's new about that statement? There's what? There's 2 things that are changing. Yeah, exactly. You've got this like these h terms, and you've got and I haven't told you what they are yet, and these u terms right here. But the idea is the x value is changing right here. Here's the x value, and the y value is changing. Both the x and y values are changing. That's going to happen if we go in a direction that is other than the partial with respect to x or the partial with respect to y. So let's parse this statement, this blue box. What's the key thing about this u component right here? What does u stand for in vector land? Unit vector. This is the first rule of Fight Club for today for this blue box. U has to be a what? Unit vector. So u is a unit vector in the direction we want to go in. U is a unit vector in the direction we want to go in. U is a unit vector in the direction we want to go in. Really easy way to do a lot of great math. That's all correct. We come up with the wrong answer is not to use a unit vector. Theoretically, it shouldn't really matter if it's a unit vector or not, right? If I say, what's the rate of change in that direction? Do I care about the magnitude of the direction? No, we're using vectors for directional purposes only. That being said, what are the two things that compose a vector? A direction and a magnitude. So first of all, we're taking all of our directions when we're doing directional derivatives as unit vectors, and we define the directional derivative f sub u with that little vector hat right there. Can you stop playing with the paper? Thank you. So u is, there they are. There's u1. u1 is the ith component of the unit vector, and u2 is the jth component of the unit vector. Fun. Very, very exciting. Now, are you going to have to do some limits? Yes. You've already been through the whole, hey, maybe there's a shorter way, and then I show you the shorter way, and then you're all excited about it. That kind of wears off after the 9th time you've done that, because now you're multivariable calculus students. So that really only works once in AB when you're like, there's got to be, maybe, and then you're all happy. You know there's a quicker way, but do you also have to use the limit definition at times? Yes, for various different reasons, not just because you're forced to. Not just because you're forced to. So what I want you to try to do right here, let's do this right here. Let's do this one right here using that. Let's do this together. So we're going to calculate the directional derivative, the rate of change of this function right here at that point in the direction of this vector right here. What's the first thing you notice about that vector that we're going to be working with? What's the first thing? What? It's not a unit vector. So what are we going to need to do, Lauren? Yeah, so our u vector is going to be our direction divided by, how do you change any vector into a unit vector without changing the direction? Divide by the magnitude, exactly. So this is going to be I plus j over what? You can speak louder than whispers. It's really okay. I want to be super respectful. Like, I have good hearing and I can kind of hear you, which means you're not talking loud enough, okay? So if we write this out, yes, we end up with 1 over root 2i plus 1 over root 2j. You with me so far, everybody? Yay. Now, you might be compelled to do something with those fractions. What's one reason sometimes you guys don't like 1 over root 2, or what have you been programmed to do in the past? Multiply by root 2 over 2, rationalize the denominator. It doesn't really matter anymore. It doesn't really matter. You can keep it like this. You just have to be able to convert between the two, because you might be given an answer that you think is incorrect, but it is correct because it hasn't been rationalized. Great. Anyway, so there's our direction. Let's use this limit definition. So if we want fu, and it's, yes, a position where I get to say fu, equals the limit as h goes to 0 of f of, what's a in this case? 1 plus what? 1 root 2 times h, yep, comma, 0 plus 1 over root 2 times minus what? F of 1, 0 all over what? H. Now you just have to be careful about plugging this stuff in. Luckily, is that a nice function right there, relatively speaking? Could that function be a lot worse? Yes, it could. If that function was much worse, you'd have to do tons of algebra, and you're like, I don't want to do that. So what do we end up here with? We end up with 1 plus 1 over root 2 h squared plus 1 over root 2 h squared minus, when you plug, what is it, 1, right? Oh, am I forgetting the limit? Is that kind of important? Yeah, a little bit. All over what? What do you have to do at this point? You have no choice but to what? What do you have to do? Yeah, expand, exactly. So you have the limit as h goes to 0 of what? 1 plus 1 over root 2h plus 1 over root 2h. I'm just doing it out like this. Plus what? H squared over what? 2 minus 1 all over what? H. Yeah, you can simplify it really quickly. Is it really easy to make mistakes on these? Super easy. What cancels and is magical and nice? Well, first, the 1's cancel. Is that magical and nice? Yes, because it means you actually do this. So we could finish it otherwise, but oh well. So what do you end up with here? Not the final answer, but you end up with the limit as h goes to 0 of 2 over root 2 plus h over 2, I think, right? The h's cancel, 1 over root 2 plus 1 over root 2 plus h over 2. So what's that going to be? 2 over root 2. And now you might want to rationalize if you wanted to, because what happens when you rationalize the denominator now? You get 2 root 2 over 2, which is root 2. Yay, exciting. Now, is this, I understand you don't really like doing this, but is it reasonable of me to ask you to do a limit like this every now and then? Sadly, yes. Come on, it's not that bad. It's not that bad. It's exciting.